Kia ora koutou. Sorry I can't be there in person with you. Instead, I'm here virtually, beamed in by the power of magic and, international infrastructure. I am going to be helping you out for a little bit here. We are talking about similar triangles, similar shapes generally, but similar triangles specifically. At the end of this, you will be responsible for pages 91 to 96. All right, so when we're done, make sure you go on to that. Well, what are similar shapes? Similar shapes are two shapes that have either been enlarged or shrunk. Yeah, and if they were to be enlarged or shrunk, they would take up the exact same amount of space. So you can see these two shapes. They are not exactly the same. Obviously, this blue one is smaller and the red one is bigger, but they are similar because if I move this one over here and I extend it to the same height, I can get one of them to cover the other exactly. Yeah, I haven't done it here. Here, we're gonna get it. Ah, exactly, right? So these two shapes are considered similar, even though they are clearly different shapes. Okay? We can move on to this next example. They don't just have to be regular shapes that we understand and know every day. They can be things like this. Again, different types of shapes, but if I was to enlarge it, I can get it to exactly fit over the top. And it's important to think about this as if you're dragging this corner, yeah? Because obviously, if I drag this, I'm changing the shape wildly. Yeah, so we don't want that. We want a shape that would only be the same if we were to drag a corner and we could completely cover it. Okay? These shapes are not similar. They are absolutely not similar because the one on the left and the one on the right clearly can't be made to fit over each other exactly. If I was to shrink this down and get the bottom line to be exactly the same on both of these triangles, then one of them would be shorter and dinkier and not as impressive. Yeah? So these two shapes are not similar. In the same vein, these two shapes, even though they are kind of weird and cloudy, yeah, they also are not similar, right? Because if I shrink this down to the width of this other shape, it's never going to be able to cover the top. Okay? Those two things are never going to be perfectly over each other. So these are not similar shapes. So again, similar shapes are ones that have exactly the same angles in each corner and have just been increased to a different way. These are similar shapes. These are not similar. They are different. Let's look at an example. This question is, are these triangles similar? Okay, and already we can see that they are facing in different directions, right? This one has the right angle in this corner, and the other one has the right angle in this corner. So they aren't in the same orientation. Oops, didn't mean to do that. They aren't in the same orientation. But are they similar? So the first thing we want to ask ourselves is are all the angles the same? Are all of these angles the same? Well, we've got the first one that we've already talked about, our right angles. So we definitely know that this right angle and this right angle are the same. So there's one angle that is definitely the same. And then if we were to rotate this whole shape in this direction, we would find out that this angle right here is the same as this angle right here. Yeah? And then finally, this 60 degrees here is the same as this 60 degrees here. So we can say, yes, all of these triangles are similar. And the reason is they have the same measurements for the angles, the same angles. Yeah, so each of these is a similar triangle. Now we can see that very clearly the lengths of the lines are different, right? If I've got my hypotenuse and my hypotenuse, those are totally different numbers. But it doesn't matter because we know that all of the angles are the same. So that's perfectly fine. Okay, let's look at a different question, okay? Lines PQ and AC are parallel to each other. So I can see that this line here is parallel to this line here. Okay, we know those two things. We also know that PQ is 12 meters, AC is 21 meters, AB is 25 meters, and we want to understand what the length of BP is. So we're looking right here at British Petroleum and trying to figure out what the length is. Now, we have been told that these are similar triangles. We know that they're similar. Okay, so our question is, how are we going to find out what British Petroleum here's length is? Yeah. Okay. So I am taking my 12 meters and my 21 meters. This is a ratio. Okay. The ratio of this distance to this distance is going to be the same as the ratio of this distance to this distance. Okay. So all we need to do is we need to make an equation that's going to be equal to each other. So the first thing I could do is I know for a fact that 12 over 21 is going to be equal to x over 25. Okay, and to make it more clear about where these numbers have come from, I've taken my 12 from here and put it right there, and I've taken my 21 from here and I put it right here. I have taken my 25 from here and I put it there, and I've taken my x, which is the variable that I've just decided, and put it right here. So I can see that I have the big under the small in each of these. It's the small triangle on top, it's the big triangle on bottom. Okay, so all of that information has been kept the same. Okay, now that I've done that, I'm just going to work out my problem here. So in order to get this 25 over to the other side of the equation, I need to multiply both sides by 25, right? All we're doing is we're doing the opposite of the things that are there. So here I'm dividing x by 25, so I'm going to multiply it by 25 to get to the next place. So I'm going to have 12 over 21 is equal, oh, my apologies, times 25 is equal to x. Okay, I'm just going to plug that into my calculator, and when I do, I'm going to find that x is equal to 14.29 to 2 decimal places. Now, am I done? I am not. What have I done wrong? You're going to look at this and you're going to shout at this screen like Dora the Explorer. That's right, I haven't put my units. Okay, 14.29 meters. Easy. We can do that again. This next question, find the missing side lengths in each pair of similar figures. Okay, so again, they've given us two similar figures, and we need to figure out how to find the values for x and y. Okay, now they've told us they're similar, they're rotated, but they're still similar. So I actually don't really like this shape. It hurts my brain. I don't like looking at this thing. So what I'm going to do is I'm going to redraw this, and I'm going to draw this in the same orientation that I've got my triangle over here. Okay, so I'm going to put my pointy bit over here and my right angle bit down here, and I'm going to say that this pointy bit is y, so I'm going to have my y over here, and this angle is z, so I'm going to put my z there, and then x is this big one, x up here. Nice. Okay, now I want to put in the rest of my values. 15 is there, it's my bottom, my base, so I'm going to have 15 there. And then I've got my x on my hypotenuse and my y here. And I'm going to write these two differently just to differentiate them from the angle values, okay? So now I've got my shape and it's looking exactly like my other shape. So now I don't have to worry about this one at all. Yeah, let's not look at that one anymore at all. Okay, so switching to a different color, we know that this side and this side are going to be the same, right? Those are the same sides of our triangle. So I'm going to put 15 over 30 is equal to, and now I have to decide which line I'm going to work on first. Okay, doesn't really matter. You can do either one you want. X comes before Y in the alphabet, so I'm going to do that first. Okay, so I'm going to put X over the top, and what's the equivalent on my big triangle? That's right, 34. Okay, so 34. And then I'm just going to go 15 divided by 30 times 34 equals X. Because remember, all I'm doing is I'm doing the opposite on both sides. So I've got here divided by 34, so I'm going to multiply by 34. And now I'm plugging it into my handy dandy calculator and I'm finding that X, oops, I've changed the color, X is equal to 17. There's no need for units because they haven't provided us any units in the problem. Okay, so let's do the same thing again, right? I'm going to put 15 over 30 is equal to, and this time I'm going to use my other figures, right? I'm going to have y over 16. And I'm going to redo my values just like I did. 30 times 16 equals y. And then I'm going to go to my handy dandy calculator, and I am going to know that y is equal to 8. Okay, and just because I like it better, I'm going to highlight my answers because that's going to help my marker look at them later on. This one is just a slightly different question, right? They want us to find out if these shapes are similar or not. And in order to do that, we're going to ask the question that I told us to ask at the beginning, which was, do they have the same angles? Are the angles for all of these shapes the same? Okay, you may not know this already, but it is important to know that the angles of a triangle always add up to 180. Okay, there's always 180 degrees in a triangle. So we can see that this and this are the same, right? But we don't necessarily know whether this one and this one are the same, or whether this one and this one are the same, right? Because there's no value actually given to us here, and there's no value given to us here, so we need to work it out for ourselves. So I am going to figure out what this value is right here. And the way I'm going to do that is I'm going to say, I know that my triangle QRS is going to have angles that add up to 180 degrees. So 180 minus 81 minus 50 is going to give us the angle of the last corner, and that is going to be 49. Yeah, so I know that this right here is 49 degrees. I am convinced now that they are similar. They are similar. But if I wanted to be double sure, I could find out what the value of this angle is as well. So I could say triangle TUV, I know that 180 minus 81 minus 49 is going to be equal to 50 degrees. So this one here is 50 degrees as well. And again, similar triangles can be rotated. So this is similar. It's just that this whole thing has been rotated, what is that, clockwise, right? So we are sure that these are similar. Okay, now going back to the beginning and reminding you what we're doing, pages 91 to 96 in your workbook is what we're going to be working on. It's been fun hanging out with you virtually. I hope you have a wonderful evening. Enjoy. Remember to like and subscribe and click that notification bell. And I don't know, YouTube. Yeah.